is 100 instructions, suppose. So you know that after 100 milliseconds, the entire thing is over.
Right, sir.
So that time you can stop applying further instructions and take a snapshot of the register values after the 100th instruction. So this $finish or those type of statements should also work with post synthesis simulations. Okay, so I think it should work. Or otherwise, if it is creating problems, then you need to stop the simulation using additional hardware control signals, like you mentioned. So does your design have a no op operation or no?
I haven't put no op operation yet.
Okay, fine. Yeah, then it's okay.
Okay.
So after 100 instructions have been executed, your program is over. There should be some statement to execute. I mean, print this is the result, final content, and that's it. After that, what happens? You need not care actually whether the registers are overwritten or whatever. But tell me one thing: why, if there are no instructions, why should registers be overwritten?
Oh,
If there are no instructions to execute, there is no further instructions to execute, why should the register content get modified? That is my question. So your final result is there in some register, right?
right.
Why should that get modified in the next, like if there is no further instruction coming in a clockless design? A clockless design only works when you feed it further stuff. So right, so the final thing it has is the final instruction you have input to it. After that, why should it keep on? Does the combinational circuit, this is a combinational circuit essentially with certain memory elements whose output values only change when you allow it to change using some enable signal, right? Does the output of a combinational circuit change if the input remains unchanged?
No, sir.
So your
Right.
PC will still keep on changing, right?
No, so you stop the changing of the PC.
Yeah, so you need a special signal for that or a special instruction for that. That's what he was saying. Parth, I guess.
Why should the
PC updates itself at every clock pulse if there are no
So suppose
instructions. So PC plus
goes,
4.
PC tries to access a certain memory location in which has not
There
been
is no code.
initialized, and there is some, I mean, unknown values probably.
Right, sir.
So
Maybe
that
0, maybe X. I don't know.
0
Depends
X,
on.
yeah, X, yeah. I mean, nobody knows what is there. So the PC collects those values because automatically it increases to PC plus 4. It collects the values, and then suppose it does some junk computation. Now, first of all, what it will do is not known, right? Because there is no guarantee that it will be a valid opcode encoding. You
Probably
get
won't.
right. But why should the register content change?
It won't. It might. If it's indeterminate, it might.
So that
Yes.
I
That's
don't
the
Yes.
problem.
need to bother about. That's
Okay,
why
sir.
I
Thank you,
was
sir.
saying at the beginning that because this was another option, you would have made it more complicated. But one option was to treat it as a one-stage pipeline kind of a design, where you have registers at the input interface and the output interface at the two boundaries. And in between, there is a large chunk of logic. The register file is clock driven. It is no longer latch implemented. It is a clock driven register file. And at every clock edge, you collect one instruction from the instruction memory, execute it, update registers if needed at the next clock edge, etc., etc. It just works like a one-stage pipeline kind of a thing. The advantage of that is you can work with synchronous flip-flops, proper standard D flip-flop type registers. The disadvantage is you now have extra register stages at the input and at the output, which is substantial because you have like the entire instruction encoding, etc. So I mean, you know that register you are, I think pipelining has been taught. So these registers at the boundaries are over it. The second advantage is that after the program has finished execution, you can simply stop the clock signal. Without the clock signal, it will not do anything. Right. So just kind of deactivate the clock signal itself after your necessary work is over. Then PC will also not update to PC+4 because the PC itself is now a clock driven register. It cannot update its value if the clock edge is not coming. Okay, so that was the other option, but anyways, this is also fine. Yeah, what you mentioned is might be a concern.
Excuse me, sir.
Yes.
Sir, I think at the end we can add a self loop instruction, like a branch instruction that will branch to itself.
You can do that. You can do that.
Sir, I had one more doubt. Like we have the KGP disk.
A dollar monitor should print the content of the register at the end. After that, if you the simulation would end.
Yes, sir.
Should end. Okay. Not bother about what is happening simulation as the.
Sir, like, is it mandatory to print the output? Like in our case, we had a KGP disk module, and then inside that the data path and all. So and the registers are actually defined in the register path, in the register file. Okay, so we can't
So
really
how does the user who has given the two numbers, are you implementing GCD calculation or what is your program?
Yes, GCD.
So how does the user who is implementing GCD computation knows about the final result? How is that provided?
One has to check the register file. There is an option that we can check the contents of the register.
I still think that you should have on your top level test bench file as explicit monitor or this type of statement.
Yeah, but then like we have to bring the registers.
Which at the end will print the value of the register. There are options available in Verilog which at exactly the time you want, only once will print the value. Like printf type statements, exactly when you want it will print the value, not the like monitor type behavior where every time the register values changes it keeps on printing, not like that.
Yes, sir, but the problem is from the test bench you can't access the registers because the registers are only defined in the register file, and there are only two output signals from the register.
Who said from test bench you cannot access the registers? There is a way to do it. The way to do it is, okay, let me write in the chat box if possible. Suppose your top level test bench is TB. Okay, then your model is a KGP risk. Okay, so TB, okay, TB you don't need to write. You can just start from this portion. Suppose the name of your module, I mean not the module type, the module, I shouldn't say the module name, the instance name is KGP risk.
Okay.
Then the name of the instance is reg file. Then inside that there is a signal called reg1.
Okay, I got
You
it.
can hierarchically write the reach the till the end using that dot operator.
Okay, sir.
KGPD's dot reg file dot reg1 is the output of register file register 1, which is inside the reg file module, which is itself inside the KGPD's module, which has been instantiated inside the TV module.
Yes, sir, got it. Thank you.
From the top level, you can reach down to any arbitrary hierarchy, any net deep inside the hierarchy.
Yes, sir.
So just check the syntax, you will find that how to print hierarchical, how to print a net name inside a Verilog hierarchy, something like that.
Okay, sir.
Excuse me, sir.
Yes.
Sir, while creating the block RAM, there is an option for enabling 32-bit addressing. So what is the purpose of it? Like, how does it work?
Enabling 32-bit addressing.
Yes, sir.
I'm not sure. Any TA who gave the presentation? Anybody is present here?
Yeah, sir. Yeah, I'm here.
Yeah, Siddhartha, can you
Yeah.
comment on this query?
Can you say the query once, Shomita?
Sir, while creating the block RAM, we get an option for enabling 32-bit addressing.
We do not need to enable it for now. It's for a different purpose. You want to use it as a data RAM or you want to use it as a instruction memory?
So like we were trying to create the instruction memory, so
Okay.
we wanted a 32-bit address for it.
32-bit address means you have that much depth.
Yes, but
Yeah.
that's not possible, I think. Like,
It's possible. Why it's not possible? Like
yeah.
you just have to give how much depth you want.
But we have to give, I think, 2
In
bit.
which mode are you using the BRAM? Like, is it in single port ROM?
Yes, sir.
Yeah, in single port ROM, you can obviously achieve that. Like, how many instructions are there?
Sir, there are not many, I think,
How
like
still?
40 or 50.
So for 40 instructions, why do you need a depth of 32-bit?
So like I want to say that the program counter has 32-bit width. So it will point
So
towards.
that is your read or write width. Your instruction length is 32-bit, right? Not your
No,
depth. Depth is different, width is different. Width is as in you are having as a whole 32 bits in your opcode. Is it
yes,
like that?
I'm saying that the program counter points to the address of the instruction which we need to fetch. So I had like in our case the program counter has 32-bit width. So the address it is pointing to will also be 32-bit wide.
You necessarily if you are using instructions up to 40, only 40 instructions you are using, you did not need to use all the 32 bits of the program counter. You can use only maybe 32, means you can use only 6 bits.
Yes.
Those 6 bits will do for you. And 32-bit addressing is a different thing, like it has got nothing to do with the depth.
Okay.
Okay.
Yes.
If you have further queries, you can send me the pictures in the Teams. I can help you with that.
Okay. Thank you, sir.
Yeah.
Yeah.
Yeah, hello.
Yeah, sir, with that 32-bit addressing, actually what was happening is that we generally do PC plus 4. But if we do not enable that signal, it just goes to the, it means it skips 3 instructions in between.
It goes to the what?
Like if I enable 32-bit addressing, then PC plus 4 works. If I do not enable it, then PC plus 1 works.
Oh, okay, okay.
Yes, the same is happening with me now.
Okay, okay. So plus 4, okay, I understood. So 4 somehow interprets that offset in terms of bytes.
4 bytes basically.
Otherwise, it interprets it in terms of 1 byte. Okay. Okay, then you enable it. Siddhartha, did you hear that?
Yeah, I heard that. So yeah, if you
is...
really require it, then you can enable. Like, but
see, one thing is in Verilog. Okay, if you are writing pure Verilog without this, without expecting that the simulator or the CAD tool would understand the byte, like the organization of the words in terms of bytes, 4 bytes at a time, you should just write PC plus 32. Because see, Verilog, the PC, the program counter increment does not understand anything. That hardware does not understand anything other than binary numbers. If you write plus 4, it understands plus 4. Okay, in assembly language programming terminology, plus 4 means 4 bytes in MIPS 32. But that is not sacrosanct across all Verilog simulators or anything. The Verilog simulators, the Verilog programming language implements hardware. Their addition is not like you will write plus 4 and it will understand plus 32. That is probably not the case. I mean, so if you do whatever is needed to make it work,
sir,
that's fine. But, I mean, I don't know.
Yeah, sir, can I say something? So
yeah, Siddhartha, please.
Yeah, so suppose your instructions that you are arranging in the COE file, it's like arranged with respect to the addresses, right? Like in 0th address there is something, then in the first address there is something, then in the second, third. So that can be accessed by PC plus 1 itself. Why do you need PC plus 4? Like it's
Sir,
a different architecture as a whole.
Our group has done that itself. We've not enabled 32-bit addressing and we do PC plus 1 itself, and it works.
Yeah, like it's standard in Verilog, but whatever you use for if you need PC plus 4, like it's not necessary, I think, in Verilog.
I mean, you are going to the PC plus 4 for what? The next data?
The next instruction.
And instructions are 32-bit weight.
Yeah. So plus 4 because MIPS 32 is byte oriented. Plus 4 basically means offset of 4 bytes.
Right. So I mean, what is their issue? I didn't get. I mean, if for next instruction you go to PC plus 4, right?
It is not working properly. That's what they say. Unless you declare the addressing mode to be 32-bit addressing mode. When they are instantiating the block RAM, I think that was the concern.
Okay, maybe then it's a property of the block RAM itself.
Yes, that's what
the
I'm
plus
saying.
1, it is internally going to interpret as a plus 4 bytes. Plus 32 bits.
Plus 32, and if you want plus 4 to designate plus 32, you have to explicitly say that I am using 32-bit addressing, something like that.
Yeah, it's like that. Like in the VRAM, if we use just PC plus 1, it will jump onto the just next address. If it is in a 0th address, it will jump onto the next address. So it's PC plus 4 or
Next word
this.
address. So
Yeah, next
basically
word.
+1 means the next word.
Yeah, right.
Okay.
So whatever be the width, it will just if it is
Just go
32,
one to one.
yeah. So we do not need to explicitly mention that.
That's fine. So then you work in that way.
Yeah.
So this is the one good point that came out in today's discussion. Second is, as I said, you can access any signal, internal signal in the hierarchy by using the dot operator and going from the top level instance name down to the whatever you want, and finally that signal name. Okay. It is slightly similar to the, say, I can give you an example, say the internet URL addressing schemes. You use the dot operator and you kind of, as you move on the left, you reach more specific parts. Here it is the reverse. As you move toward the right, you go deep inside the hierarchy. And thirdly is, I would strongly suggest, to make it easier for the TAs to grade your work, write your test bench in a way so that after your program has completed execution, whatever is the length of the program, 50 instructions, 100 instructions, whatever, the result of the final computation should be visible. It can be visible either on a waveform viewer, or I would suggest make it visible explicitly in the log file using a controlled print statement type of a thing. Controlled print statement in a sense that, say, after sufficient amount of time, you only need to print it once when you know that the result has been computed by now. And don't bother about what happens to the internal state of the machine after that. So your simulation basically finishes there. Physically, what happens to the circuit, don't bother about that. So your lab test will be on Friday. There will be only one problem. It will be a problem that will require you to implement the data path and the control path of a very, very simple, small mathematical algorithm. The algorithm will be described and you need to implement that algorithm in Verilog and write a test bench to simulate it. Okay. Now, those who have odd roll numbers and those who have even roll numbers will work on separate problems, very similar problems of similar complexity, but separate problems, so that there will be two versions of the question paper. When you get the question paper, clear instructions will be given that this is for the odd number students, odd number roll number students, and this question paper is for even number roll number students. So you attempt only one of them according to your roll number. Each of you solve the test individually, submit in a one single zip folder your test bench file and your design files. Okay. And the complexity of the problem is such that it should be comfortably solvable in 2 hours. I mean, it is a really simple problem. Okay, so those of you who have by now performed considerable amount of Verilog coding, you have solved the assignments by yourself without much external help or copying from other groups, etc. You should have no problem in solving it. However, those of you who have probably been a little lazy and haven't put out much effort in solving your lab assignments by yourself, and at the last moment you have tried to get resources from other students, copy pasted their code or found code on the internet and copy pasted, etc., you will have trouble solving it in 2 hours. Okay, so that is expected. That is how we differentiate between serious students and not so serious students. But it's nothing like it's a very lengthy problem which cannot be solved in 2 hours. It won't be like that. This much I can tell you. Okay, so any other questions? Today is basically the last day of class in the lab. So if you have any further doubts, etc., please clarify. The deadline for submission is 13th. So 13th midnight. So Saturday midnight. But we won't be meeting again to discuss this assignment issue. So if you have any issue, please clarify right now. Also, those in the theory class, all of you, I believe, maybe other than 1 or 2 students, all of you are also in the theory course. You already know, you have been informed, your third written exam will be on 15th. Okay, another thing I wanted to tell you is I have received a query from Intel about whether you are finding time to work on the One API stuff, because they arranged a competition specially for you. Usually they do not arrange any competition with prizes. This time they did. So they will extend the deadline till maybe January or February, something like that. I have discussed this with them. They said they will consider it. So so once your semesters are over and your internship exams, selection, etc. are over, I don't know whether you are having them this time, you should be in a position to work on it if you are interested. It's very interesting technology. I mean, they are giving you access to a cutting edge HPC infrastructure, which as such is quite expensive, but they are giving you for free. Try to use it, try to develop the skill set if you are interested. It's good. This much I can tell you. And also the teachers, we hope you liked the lab. This lab is of a different, slightly different flavor. It teaches you to actual how computer systems are implemented, and which is important to understand, we believe, for you to be successful computer scientists. Okay. Eventually everything runs on silicon, and if you do not understand the schemes by which modern complicated integrated circuits are implemented, designed and implemented, it's your understanding would probably be unclear. Okay, any more questions?
Sir, will we be dealing with this program in the coming test, lab test?
Which program?
This blockram, sir. In ISC we are using.
Oh, in the lab
module.
test? No. Lab test will be a regular Verilog programming with just test bench. No, there no blockram will be necessary.
Yes, sir. Thank you, sir.
Sir, hello.
Yes.
Yeah. So in the submission, we will just attach the COE files and during
COE
evaluation.
file, test bench files, your documentation, your main module files, etc.
And the XCO file, the block RAMs.
Yes. Block RAM file also, yeah, okay.
So those will be loaded during evaluation, right?
Yes.
Yeah.
Because you see, your the question paper at least does not mandate a separate test bench for each module, right? I suggested that you do it for I mean that would help yourself in debugging the every module, but as such it is not mandated. The entire evaluation is based on whether the COE file that you will generate that gets loaded onto block RAM and it executes properly to give you the final correct result. So whatever is needed to perform that process, you have to submit all those things.
So any batch, any batch could complete, like this assignment as of now.
Till now, anybody has completed?
Yes, sir. Like
Yes,
this is
sir.
Group
1.
Okay, very good.
Good.
So you were able to find out the sorting, essentially execute the sorting on your target FPGA. I mean on your processor.
Sir, like your voice cracked for a second. Can you repeat again?
Yeah, so you were able to kind of perform the entire sorting algorithm and execute the instructions one by one on your design processor.
Yes, sir. Like we implemented 2 algorithms. One is binary search and one is the GCD algorithm.
Okay, that's pretty good. Okay, so you could get the and this simulation, you are doing a simulation which is like post route. Like, are you doing the final simulation?
Yes, sir.
Okay. Okay, that's very good to know. So any other batch also could do this work? Okay, so
Sir,
yeah.
Sir, this is Rajat from group 46. We've implemented the GCD function as well, and we are getting our results. We are getting correct results, and we've done the simulation also, and it's working on the FPGA.
Okay, okay. That's good. Very good. Okay. Any other group?
So we have implemented the GCD one. GCD one is working. So we are planning to implement maybe one more algorithm.
Okay, okay.
Good.
That's nice. So more groups.
So, am I audible?
Yeah, you're audible.
So this is group number 36, Yashika.
Okay.
We have also completed the simulation on GCD.
Okay, okay. Very good. So you are able to do a post-route simulation of your processor?
Yes, sir.
Okay.
We will debug it today once, like on more algorithms, so that we are sure.
So so those who are planning to implement the second algorithm, what do you want to implement? Sorting. I mean, what is your plan?
No,
Sorting or maybe linear search.
Linear search, okay. And
you can try to run any algorithm as such. Actually,
anything that you have solved so many problems in MIPS.
Since you have actually done one of the things like the GCD in particular, you are free to like explore and like run any algorithm and see that whether even if it's a small algorithm, I mean, it would be fun to see if all the groups are trying something different actually.
Try to implement an algorithm with function calls, etc. if possible. That will check whether your stack, etc. are working. You have already done that a lot of assignments like that when you did assembly language programming. So try to do that in this also. That will be nice.
Yeah, I would. Yeah, so you are you are free to basically the idea is that you are free to kind of think on your own, and as long as you see that your processor is able to execute a sequence of instructions, that gives you the liberty of trying various alternatives. So I leave it to you to think about like if what kind of alterations you can, but definitely it's a good starting point since you have some of the groups have finished. That's very satisfying, I would say. Okay.
Yes.
And also, I mean, those as all the groups actually, those who have finished and those who will be finishing this, I think you have every reason to feel very satisfied and very proud. So if you look back at the assignment, you have been given a custom RISC instruction set, and you have been able to implement algorithms mapping, which run on that type of a processor. It's a toy processor, no doubt. It does not have that many instructions. It is quite simple, but still it's a full-fledged processor which can perform more or less any operation. Okay, so you have every reason to feel very proud if you when you complete this assignment. So if somebody writes a compiler targeting this processor, essentially
Adesi, we cannot hear you.
Yeah, I think there's a network cut. Okay, so that's great. So any other group would like to share, like even if it is partially done, like could you essentially finish?
Hello, can you hear me?
Yes, we lost your voice for some time.
Oh, okay. So I was saying that if somebody implements a compiler targeting this processor, then basically you have the entire toolchain for this particular processor. And then if this processor is enhanced to support some other stuff like interrupt handling, etc., then theoretically you have an entire, and maybe a floating point unit, etc., then you have theoretically you have an entire modern computer system, okay, which you have implemented yourself, right? So that's something to be very proud of.
Sir, I wanted to clarify one thing actually. Professor Devdeep talked about post-route simulation. So I just wanted to clarify whether it's the same thing that I am thinking it is. So once we do the synthesis and then the software says that it's mapping and it's doing post-routing, mapping, translating, and then implementing, which involves the post-routing. So once all these processes are done, if we do the simulation on iSim after that, if we simulate our test benches, that is the post-route simulation, right?
Yeah, so you will see that after or doing all these steps, right, you will see that there is a netlist which gets generated actually. Okay. So
Yes.
therefore, when you click for the simulation, the interface keeps on changing, but at least what I would expect is that there are different types of simulations that will be offered to you. You can do behavioral simulation, you can do a post map simulation, you can do a post translate simulation, and finally it's a post route simulation where the routing is also done. Okay, so if you click that option, then that is the most like realistic simulation, because not only the delays for the components are inferred, but also the routing delays are also accommodated in that simulation. Okay, so that is the closest that you can expect from an actual hardware device. So, is Siddhartha there on the call?
Yes, sir. Yeah.
So Siddhartha, can you please confirm this point, because you
yeah.
the interface better now, so that's why.
Yeah. So like whenever you implement, like perform the final implementation, and if it is like no warnings are there, then you can go for this post implementation simulation is there in the like whenever you click on the check button of this simulation, there will be an option there. There will be post implementation simulation, and there is also something known as post synthesis simulation. And there are two parts of that. There is post synthesis functional simulation. There is post synthesis timing simulation. And similarly, for after implementation, there is post implementation functional simulation and post implementation timing simulation. So all these simulations should give you the correct result, irrespective of whatever your behavioral simulation gives. So if
Yeah,
your
so-
design is correct, all the implementation.
Given the time crunch and other things, I'm sure you have other works to do. But what I would recommend is that try one post implementation simulation. Like out of the functional and timing, at least try the post functional, post implementation functional simulation.
Yeah, functional simulation will actually run quite fast rather than timing simulation. So
yeah, that is why I'm saying that try that
Yeah.
and see that it gives you the correct result as you had got probably in your behavioral simulation. If you have already done that, it is fine, but otherwise maybe you would like to check that.
Okay, sir.
Any other group? Okay, so I believe that most of the groups are working and
Working on it, yes.
even if it's not completely done, you are almost there. So that would be, it would be nice to get it finished and so that we can bring our lab to a logical end. Okay, I have no other points, Rajat. So maybe if it is done,
Can wrap up. Okay, students, thank you. And so do you want us, so your exam will be from 2 to 4 on Friday. Do you want us, the teachers, to be present after 4 on Friday to again like discuss some stuff or doubt clearing or anything? Or if you want, we can be present. Otherwise, we can wrap up and you can email us your queries or post on Teams, whatever. So Devdipta, what to do? So on Friday, should we again come online after 4 or?
It's okay. I think. I mean, if there are no other questions, then I think we can just leave it. I mean, we can. Our exam is what we need to basically have our focus probably next. So I think it's okay. I mean, we can probably even leave and give give a like leave next week. I mean, next class also if you want. I mean, it all depends on the students. If you want to interact, we are there. We can definitely come over and have a chat. But if you think that you have already understood all the questions, the doubts are cleared, and you just need time to finish the assignment, then I think it's better. We just give. I mean, you can carry on and continue on your work.
Yes. Okay. So then in that case, thank you for your participation in the class. We hope you enjoyed it. And best of luck for your lab test, and all other theory subject exams that will be probably be happening next week. Thank you. Okay. So
thank you. Bye bye. Hope you have learned something new. Bye. Thank you.
Bye bye.
Bye.
Thank you, sir.
Thank you, sir.